least I got through the embarrassing part without recording it.
I timed that well, right?
Yeah, perfectly timed, exactly. It's like, so what was Dr. Terrell talking about? Oh, he was talking about science. Oh, yeah, right.
Wow, that was such brilliant insight, Dr. Terrell. Thank you for sharing that with us. You can put it on the recording later for the people who missed it.
Oh God. Hey, I learned something the other day though.
What did you learn?
I was looking on a YouTube site, and it was a World War II thing. And they were talking about radar, and they were talking about ways of making microwaves for radar, right? And they started going through these cavities and stuff that they use. And they said, oh, and this is called the Hall magnetron. And I knew that one of my ancestors on my mom's side was involved in making the microwave, in making the magnetron. But I had never heard the name there. So I thought, oh, that's cool, man. Somebody in my ancestry was actually smart. I don't know how it skipped me, but anyway.
Nah, it's there. You just like to hide it on occasion. But sometimes it sneaks out and you don't even realize it.
It's so weird though. Like, there's so many ways that I'm such a dope. Oh God. You know, some ways I'm brilliant, and some ways I'm just an idiot. And it's like all the important ways in terms of department function, I'm an idiot. So I'm constantly apologizing to our chair, Dr. Singmaster. Oh, I got called out so bad in this email. She's very diplomatic, right? But she was saying like, you know, next time, don't come late to the recruiting meeting. I'm like, and don't turn off your video. It's rude. I'm like, oh, geez. Oh, man, that was me. So I said, sorry. Anyway, I'll be all right. It's like, it's nice not to be easily fireable. But, okay, so let's talk about equilibria here. I'm going to try to share a screen here. So, and I'm gonna do a problem, I hope, from this set here. Let me see if these work. Yeah, see, I gotta re-log in here. So you guys are gonna laugh, right? I'm gonna go to chapter 19, and it's not gonna have. These are all the problems that I have for chapter 19. I cannot find anything else because it's like you delete them and they go away. So the one that I'm thinking about is this one right here, spectroscopic determination of pKa. And I will make this larger, etc., for y'all to see. Why don't I just dive into this one? So I'm just going to share this guy. Okay. So so I hope you guys can see this okay. And this is one of the homework problems that I assigned, and I actually understood when I assigned it, so I can talk about it. But and it actually got really tricky at a certain point, and it probably didn't fool you guys, but it fooled the heck out of me. So Casey, you've done this one all right? Yeah.
Yeah.
You did this one too, Cindy? Or not yet? Not sure.
Nope, not yet.
Okay, all right. So Casey, you're just gonna have to bite your tongue for a little while.
This is one of the ones that made me not want to throw my computer out the window, but all of the rest of them did.
Oh, got it. Yeah. I'm really, the solver is very idiosyncratic, and you have to have the numbers all set up just right, because what it does is it starts changing shit, and looking for a solution, and it doesn't care if concentrations are negative. it tries it. Say, oh, what about minus 2.3 molar? Even though that's non-physical, right? And so sometimes it just diverges and can't find a solution. Sometimes it converges on nonsense. So I'll talk. If you send me that one by email, I will do it, and I promise I'll come up with a solution. But it's not in the homework.
The thing with this one, I remember, is that you have to omit 2 data points.
Oh, right. Oh, this one. Yeah, this one.
Yeah.
You have to omit the first and the last, right?
Yeah.
Yeah. They use them as yeah. See what this is. This one basically is about is that there's a high pH and a low pH form of this indicator, right? And we're basically just titrating it, And what we're trying to do is get the pKa from all this pH and absorbance data. And when I walked through this, I got real confused because I paid too close of attention, right? And then there's a leap here that says these expressions can be combined to form the expression down here. I was looking at that thinking, that's not right. That didn't seem right. But the thing is that this AHIN, this is the total absorbance when everything is in the protonated form. So that corresponds to this giant leap from 475 to 1.67 pH down here, right? And the absorbance goes way down to 0.004. So when you go through this problem, you take this point, this one, and this one, right? The ones between 4 and 6 here, right? Then you use these outliers 1 and 12 to place these boundaries, AHIN and AIN minus, in your data. And so the idea is that when you're trying to get the log of the concentration ratio, all you really need are these bounding absorbances and then the absorbance in between. And so you'll recognize this expression down here. pH equals pK plus log of, and this should be A minus over HA, right? And the A minus form, is, they're saying it's proportional to this amount right here. If we're at this absorbance right here, and these are the extremes, then they're saying that the ratio of A minus over HA is equal to this absorbance divided by this absorbance difference, right? So you can do those absorbance differences, and then let me grab that file real quick. And I'll show you how I did it. I know that it's probably like not that huge a deal for y'all, but let's see. I'm going to switch over my view to, here it is. This guy, share. So there we go. So here's the absorbance between these boundaries, right? And these are just numbers here. And then this one here, this is this minus this. This is this minus this, etc., right? And this is this minus this, right? And this is the negative log of that ratio. And the idea is that if you plot these out here, there's basically there's an easy way and a hard way to find the answer. And the hard way is the way they show you, which is just awful. I think it's just awful. But what they do is they say, okay, in this plot, right, you're basically going back to this equation. Let me write it out here. That pH equals pK plus log of A minus over HA, right? I don't know if you guys can see that or not. But, and they're saying that you want pK, right? And if you plot it as this log versus, I'm sorry, pH versus this log function here, right? Then pK is what you're looking for. That's the intercept, right? But that's not what they do. For some reason, they put pH on the x-axis, right? And this derived thing on the y-axis. So you got to solve for the x-intercept, right? Well, when you do that, this is just, it's just minus b over m is the x-intercept there. And that gives you 5.3. And that's the correct answer for pKa. But it's just also just the intercept if you plot it the other way around. So this was just a weird one. It's not really hard. And it didn't frustrate Casey, so I don't know why I'm even teaching it, you know. But Nicholas, you bumped up against the solver issue too, right?
I'm not sure if that's the problem I had.
Oh no, this is not the problem. This is not the problem. You
I know, but I don't know if that's what.
Yeah, you had a solver issue. And I completely get, in general, what the solver thing is trying to do. Well, in a very general way, let's say. But I can't find the problem. I don't know if you were here for that diatribe, but I lost all those problems. When I went through and I trimmed down this problem set, I removed that problem, right? Oops. And that problem is no longer in the list that I have here. So I don't even know what to do about it. Did you have more than 19 problems in the data in the set that you worked on, Nicholas? It was just 19?
Yes.
Can you recognize fluorescence quenching, Stern-Volmer, effective pH on quenching, derivatization, path law, spectroscopic determination? That's the one we just did. Isospastic points, concentration in pKa. Yeah, is this one? No, this is a simple one because they give you epsilon for both cases. I think I did this one in lecture last time. Did I not? So I don't know.
This is the one that I was struggling with.
Oh, this one?
Yeah. Unless you did it, I don't. Wait. Oh, there might be a closely related one.
Yeah, there's probably a closely related one because this is kind of a closed. This is pretty closed form. I think it's like a medium difficulty one. And I don't think you would really struggle with this one. So, let's see here. Yeah, I mean, you go earlier here. We can go through every single one, right? This one, ligand X, copper. We did all this. These are these are just two equations.
That's
two
the
unknowns.
solver question.
Oh, this one is.
Yeah.
This one is. Oh, I used Linest. For this, guys. I did it in lecture.
That last night. Yeah, it's on the video, Casey.
Yeah, I did this one using Linest. Yeah, so
and it is a mess.
Sapling was like, you only have this one way to solve it, and it's solver.
Really? That stinks. Because this is classic Linest stuff. And I got the right answer using Linest. I know I did. So let's see here. How can I solve this using solver? Is this the solver one you hit, Nicholas? Do you think?
No.
No, you had a PK one, right?
Yeah, I'm pretty sure it was the one that you said was medium difficulty.
Oh, really? The one with the epsilons?
Yeah.
Okay. Well, let me do that one then. Because that's not so hard. Okay. It wasn't this one, right? Wait, it was this one.
It is.
I get this one. Okay.
Wait, no. That's just... No, it was the other one you were looking at where it asks for pH.
Okay.
And, yeah.
Okay, this one maybe?
Mm-hmm.
Okay, let me see if I did this one. I might not have done it. Let's see. I don't think I did this one on paper. Maybe I did it in Linux or in Excel rather. But let's just talk about it for a second. I need to study it first. A mixture prepares you 30 mils of 0.07 molar weak base, pK of 4.6, 30 mils of 0.05 molar weak acid, pK of 3.1, and 1 mil of 10 minus 4 molar HIN, an indicator, and then that into 1 mil. HIN is a program indicator. Let me see. Molar absorptivity values for HIN. Let's see. What's the pH of this solution? Okay. So let me take a stab at this puppy. I haven't done this one yet, so maybe you'll get to see me fall on my face. But let me write down the vital stats here on a piece of paper and then we'll get to it. Have you done this one yet, Casey? Yeah. I'm sorry. This
it's okay.
is, I apologize. I'm sort of like behind you guys. Okay. This is 3.0 mLs, 0.06 0.67 or 607. Acid. 3.0 mLs. 0.0503 pK. 2.1, and then indicator 1 mil. Indicator 0.000 into 8. And then the whole thing is QS to 100 mils. A at 500 is equal to, or A at 550, really? Okay, 5 centimeters south. It's epsilon BC, which is 0.1162. B equals 5 centimeters. And A will equal IN minus as epsilon 2.26 times 10 to the minus 4 per centimeter. AHIN epsilon is HIN minus epsilon 1.53 times 10 to the plus 4 percent. Okay. What is the pH? Okay. So let me change the share over here. So there's an acid-base conjugate right here, a conjugate acid. Oh wait, no. Holy shit, these are not conjugate. Sorry. Let me look back at the spell just a quick second. Where's the pH? Oh, I see. So these are actually unimportant, but they're buffers, right? The important thing is the indicator here, and the indicator is 1.28 times 10 to the minus 4 molar times 1 milliliter, and that's diluted to 100 mLs. So this is 1.28 times 10 to the minus 6 molar. Right? Now this guy here is divided into 2 parts. Right? So we have two extremes. We've got A for the HIN, A for the IN minus. It's probably reversed there. No, it's actually fine. This is fine. And then we've got A for the solution. Right? So what we need to do is compute the the absorbance of pure HIN and pure IN minus. I'm going to refocus this here. There we go. Of these guys. So A for the HIN here is going to be 2.26 times 10 to the minus 4. 10 to the plus 4 times 1.28 times 10 to the minus 6. This is molar. This is molar centimeter, and then times. Let's do this whole thing as though it were 5 centimeters, right? Centimeters. And we can do the IN minus. That's going to be 1.53 times 10 to the 4. Times 1.28 times 10 to the minus 6 molar times 5 centimeters, right? And then the pH of the solution will equal to pKa plus the log of, it's this quotient here that it's going to be, I think it's going to be A minus AIN minus over AHA minus AA. It's this trick that uses the ratio of those guys, the extremes, as a surrogate for HA and A minus. And I just saw another wrinkle here, didn't I? Which is PK. And we don't know the PK for the stupid friggin' die. Do we? Oh my gosh. Okay. Let's cheat. I know what to do. Hold on. Let's cheat our way out of this one. So, I just realized that I can't solve this because I don't know the pK of the dye, right? They give the pK of the weak base and the weak acid, but I was solving this as though I knew pK of the dye, and I don't know that. So let's see what they do. Yeah, and then eventually you solve for that guy. Let's see here. We say show feedback. Show feedback. I see. You can get to this using the ratio of the K's. Got it. Okay. 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 So let's do this. So, we'll start by determining. This is how I get through this course, you guys. I cheat. They give the answers in the book. Let's see. So, B plus HA makes BH plus A minus. And K is the products of the reaction. And then, since they give pKa in both cases, what do they get? KW. That's KW over KW. So the A will be K3, dude. What's K3, dude? I can't read this. So basically, K here is equal to 10 to the minus pKa over 10 to the minus pKa. Or pKa for the acid and for the base. Yeah, how they wound up with KW in the numerator and the denominator here. They're making the second substitution for KB. It's KW over KA, I guess. I don't get that. In the end, though, it has got to be just the ratio of those two guys, right? 10 to the minus 3 over 10 to the minus 4.6. Mm-hmm. 181 over 10 to the minus 4.607. gotta do a trick here. Ah, didn't work. Oh, shit. Oh well. You know what? I have to get back to you on this one because I don't know the answer.
I can send you how I did it.
Oh my God, would you? That would be awesome.
Okay.
Thank you. Ah. Okay. Well, what else should we do today? We can do more. We can do more problems, or we can go through the notes, whichever you
Dr.
guys.
T?
Fook.
Yes, hello.
Hello.
Can
How
we
are
go?
you?
Can we go over 17? Question 17
17.
about the antibody thing?
Oh, sure. Yeah.
Yes, that one. Oh,
Oh,
sure.
okay. Sure. This is how ELISA works, basically. ELISA requires two antibodies to the same antigen. Right. The antigen here is the analyte. So one of the cool things about biochem is that you get to steal from nature, and the more egregious a thief you are, the better you look, and the better you are. Right? So in this case, you have your analyte and your antigen here, and there's two antibodies for it. There's this one that's like a pink Y, and then the other one is this enzyme-linked antibody, which is this guy here, right? So there's two things that are borrowed from nature. This antibody and this antibody. These are just stolen from rabbits. Rabbits that you shoot up with this analyte, and they generate this antibody and they generate this antibody. And, and then you somehow clone these antibodies. And I'm not exactly sure how you do this, but I know that you harvest the antibodies from rabbits, right? That you've inoculated with this analyte, or antigen analyte, right? So first you take a polymer. It's a little micro well, and you link an antibody to it, and then you generate the second antibody. You link an enzyme to it, and this is probably horseradish peroxidase, or something that can produce a fluorescent product really fast, right? And the idea here is that when this antibody is present, first it will bind to the polymer support. Then you rinse it really well. And then you put in this second antibody solution, right? The second antibody solution has this enzyme here. So now you have a sandwich. It's polymer, antibody, antigen, antibody, enzyme. So now you have a surface that has an enzymatic action, and the enzymatic action is what reveals the presence of this sandwich. And this sandwich depends on all of the parts being present. The antibody, this antigen, or this analyte, and then this antibody and this enzyme, right? And these are linked together, of course. So first you take an antibody that's specific for the analyte, and it's bound to the support. So that's the first step. Second step is you take a sample containing the analyte, and you incubate these together, meaning you mix this in here and you shake it for a while, like at room temperature, and you give this binding time to happen, right? And ideally, what will happen is that there will be some saturation binding of the antibodies on the support, right? So you're not gonna tie up every single antibody, right, on the surface. And then you wash it. That removes everything else except for this bound sandwich, right? And then you put in the antibody dye, or antibody enzyme linkage here, right? And this guy here goes in, you incubate it, you shake it for, you know, a good several hours or something. And you give this guy time to bind, and then you wash it again. And you introduce this non-fluorescent analyte, and you get a fluorescent product out. And this is the order of the steps, basically, you know, that you need to go through in order to do an ELISA. And I think, you know, ELISA it's a product really of a lot of technology, because you need a bunch of ingredients here. First, you need 2 different antibodies for your analyte. These different antibodies have to bind to different parts of the analyte. So, you know, that's not always easy, I'm sure, right? And then this second enzyme has, you know, you have to link it to an enzyme that can produce a fluorescent product, you know. And so the last step here is basically the kinetics of the transformation from non-fluorescent to fluorescent, right? So if this enzyme turns over 1,000 per second, and you give it 1,000 seconds, then you'll get 1,000,000 fluorescent products per sandwich, right? And it's so you give it a starting point and an end point in time to do this last reaction. So that's the story of ELISA, you know. Just as one sort of footnote on this, instead of a fluorescent enzyme product here, you can also use, if you want, a radionuclide. Oh, excuse me. Oh, sorry. I'm gonna sneeze. Sorry. Or you can use a fluorescent enzyme here. And both of those can serve to image these sandwiches, right? But it's the support, analyte, wash, second antibody, and then image. It's this process that gives great specificity. So you've got to get these 2 antibodies to bind. Is that too much, Luke?
I got it.
Yeah?
I got it.
You didn't give me an easy question because you felt sorry for me?
Wait, what?
That's okay. I was asking if you gave me an easy question because you felt sorry for me.
May we go question 15 and 16 if possible?
Sure. You're ripping through these puppies. Okay. Let's see here. 15.
That was warm up.
Right. Okay. Thank you. All right. So, okay. So this is a good one. These are the steps in quenching, right? So oxygen is an interesting entity because it's a ground state triplet, right? I don't know if you guys have had Chem 145, but you know, and also Chem 161B, they might touch on this too. But oxygen O2 it has a very strange bonding scheme, and it is a ground state triplet. So, you know, everything that's floating around is potentially a good quencher for luminescence, because most luminescence comes from triplet states. So, you know, ruthenium in the singlet state can absorb radiation, and then it'll be triplet. And then the triplet can transfer energy to oxygen. And this, there's a variety of mechanisms, or there's two mechanisms that I've heard of. There's Dexter and Forster, and the Forster mechanism is dipolar. And basically, these two triplets come into, you know, 1 to 5 nanometer radius of one another. And it's simply the case that there's the energy of one can transfer to the energy of the other. So there's a similar state energy difference between singlet and triplet in the ruthenium complex and the oxygen. Then the ruthenium excited singlet can relax to a triplet state, and then the oxygen can excite to a singlet state. And so you're left with ground state ruthenium triplet and excited state oxygen singlet. And then the ruthenium triplet state it'll be on a much slower decay pathway, and there's a higher likelihood that it will decay non-radiatively, and the overall effect is that there's less luminescence from the ruthenium after it interacts with the oxygen. So there is actually a decent picture of this in the notes. Let me find that for you. Let's see. This is past spectrophotometric reactions and all the way into there you go, fluorescence. Yeah, I think it's the Oye-Jablonski diagram shown here. So hold on. So it's similar to this quenching, this internal quenching scheme here, where the triplet or the singlet excited state interacts with triplet oxygen, makes singlet oxygen, and then the triplet, it's not going to like this. Sorry. I'm going to write it down. But anyway, actually, I'm not going to write it down. Let's just talk about this case here. This is fluorescence detection using an interesting molecule that was designed for cyanide detection, right? And this molecule is called a Fluorogen. And a Fluorogen is a molecule that becomes fluorescent in the presence of a certain analyte. So there's a couple ways for this molecule to quench, and all these squiggly arrows down are quenching, right? They're non-radiative decay from this upper vibrational state down to the ground state. So, these are labeled aromatic hydrocarbon and aldehyde, and what they're referring to is that MOs that are somewhat more centered on this aldehyde group here can take excited state energy from this conjugated backbone, and there's mechanism by which it can relax then to the excited vibrational states of this backbone. Now, if this guy interacts with cyanide, however, cyanide nucleophilically adds to this oxygen, then that adds that hydrogen, and then you just get a little bit of a charge shift here. And then this becomes this system becomes non-conjugated. There's a conjugate on the CN, right? It's C triple bond N, but it's not actually conjugated in because there's two single bonds. So this group here does not have the deactivation pathway that was present when this was an aldehyde. So by adding cyanide, you increase the fluorescence of this compound. And so this is, the type of thing that you can look for cyanide for, where you could spray a surface, right? And if the surface becomes fluorescent afterwards, there's a very good chance it has cyanide, right? Because cyanide is very specific for this aldehyde. And so if cyanide is present, it will cause this molecule to increase in fluorescence. So this is a trick that you could put into your forensics toolkit, for detecting cyanide. Now, and it's similar in theory to this whole business with oxygen quenching. However, this is the opposite, right? This is the quencher is internal, and then cyanide comes in, and it causes the whole molecule to be more likely to relax. Yeah. So what was your other question, Fink? Just go on through 1 through 19?
No, 16.
Okay. Let's see here. Let's see. So we're 16. Okay. Okay. This is a quenching problem. Oops. So the idea is which are suitable donor-acceptor pairs to use in this set of dyes, right? So the idea here is that you need, for the emission profile of this guy, to overlap with the absorption profile.
Dr. T.
Yes.
I think share the previous screen from the
Oh,
last
sorry. Oops. Yes, I am. Sorry. So, sorry about that. So this is a case where the emission from the donor has to overlap the absorption from the acceptor, right? And even though there may not be, free space photons involved in this transfer, that's still true. So for example, then, to use 405 in a donor-acceptor pair, you probably have to use 488 for the acceptor, right? Because this emission is fairly blue, and this excitation is fairly blue. So let's see if that's true. 485. Oh, okay. Oh, I see. Analytical objective. Okay, this is a little bit more specific. Excitation at 488 results in little fluorescence 600 when the dyes are apart and strong when they're close. So this is a shift from 488 to 600. So all we have to do is see, well, which of these emits strongly around 600, right? And which absorbs strongly around 488, right? So Alexa Fluor 488 has a strong band here at 488, right? And then the absorption around 600 could be this QSY21, for example, or 555. Yeah, right. This guy, this emission, or this, oh my God. Right. The emission of this guy is around 600, right? Around 600. So I think it might work. Oh no, that's because the absorption is out here. So 488 is the absorption, and then the transmission of the energy goes from excitation to emission to excitation to emission, right? This emits here, this is excited in that range, and then this emits here. So right around 600 here is where the emission, excitation, emission, that handoff of energy occurs from all the way from 488 to say 600 over here. So that's why the 488 goes to 555. And then let's see here. And then 520 is the QSY9. Why would QSY9 have any emission? I'm not sure about that. This says absorption, but doesn't say emission. I see, it's when they're apart, right? So this can quench the 488, but when they're apart, this will emit at 520, right? This is 600, this is 520. So this is the native emission from the Alexa Fluor 488, right? Does that make sense?
Yeah, I've been listening. I have been listening.
Does that make sense to you, Casey?
Yeah, I did that one already.
Okay, got it. Thank you. Cindy, does it make sense to you? Or are you like done with this shit?
Yeah, no, that looks okay.
Okay. Yeah, so it's basically excitation to emission, emission to excitation, excitation to emission, right? So you can and there's fluorescent and there's non-fluorescent dyes, right? The fluorescent can result in these large stoke shifts, say from 488 to 600, right? Normally it'd be like 488 to like 550 or something, you know? But then you just add a second dye in here and you can get it to go from 48 to 600. Or you can get it to go from 488 to nowhere, right? It'll just be absorbed when they're close. And this is the second case. Then the third case is excitation at 532. That's a nice green line. And it's either at 670 or 570. So 555 and 647, right? So it absorbs here and it emits here when they're close. It absorbs, emits absorbs and emits here when they're close, right? The first one's when they're far. When the 555 and the 647 are close, and the emission from this guy can excite this one, and that one will emit in the 650 range. Right? So anyway, this is just examples of choosing these pairs of dyes for fluorescence resonance energy transfer purposes. Okay, guys, what's next? Shall we say bye?
Can we do 13?
Can we do 13? Oh, let me do 13 next time. It's basically it's a Stern-Volmer quenching plot, right? And see, if you remove it here, it's gone for good. Anyway, but yeah, if we let me do that one next time, if that's all right with you.
Yes.
All right. Okay, guys. I think I've had enough. I'm sorry today was kind of sucky, but I'll do a better job Tuesday, I think. All righty.
Thank you, Dr. T.
Thank you, guys. Thanks for coming.
Thank you.
You, Dr. T.
You.
Bye. Bye, my tiny class.